Hello, everybody, and welcome to our next talk. And please welcome Janna Burman, an associate professor in computer science at Paris-Saclay University. And the talk, self-stabilizing population protocols. Hello, Janna. How are you?
Hello. hello. Yeah.
What is the weather like in Paris right now?
That's very good. No rain. So that seems fine. Not cold, not too hot yet. So that's fine. And in St. Petersburg, how it is?
I'm in Yerevan right now, and it seems pretty hot. It's like 30 plus degrees Celsius. I just can't take it anymore. So we have a nice 1 hour. When I first read through your slides, this subject seemed very interesting for me. So let's move on to the talk.
Okay, great. Okay, so I maybe start with a very general description of my talk to put you into the subject. So this is about distributed algorithms. So in this field, we are interested in studying fundamental problems, meaning problems which serve as building blocks in distributed systems, in the applications like internet, mobile sensor networks, or other sensor networks. So we study such important problems that we extract from these applications, from these systems, and we are interested to study them formally. This is the important point here. So we model the system in question in a formal way. We define formally the problem that we want to solve, and we then, of course, we design solutions for the problem, and we are interested to analyze them in terms of correctness and complexity in a formal, in a mathematical way. So in this talk, I will focus in a particular distributed computing model, which is called population protocols. So we design also such protocols in this model, in the type of system it represents. So population protocols actually have two senses. Yeah. And in particular, the second focus of this talk is on self-stabilization. So my goal will be to present you protocols following this approach of self-stabilization, which is a fault tolerance approach. Okay, so this is just a general view of the talk, and I will start right away with by the description of this model, what actually population protocols describe, which type of systems. Okay, so in this model, we consider a collection of computational and communicating nodes, which we call agents. This collection is of size donated, for example, by big N. The size of the population is can be unknown to the agents, to the nodes themselves. These nodes, these agents are indistinguishable a priori. They are anonymous. They don't have any identifiers, and they have originally also finite or even constant state memory. Okay, so how they cooperate, how they communicate. They actually interact in almost unpredictable and asynchronous way in pairs. So we imagine that each time, at each step, two agents come close to each other. They exchange their internal states, and they move to two new states according to a transition function, which in fact represents the protocol. Okay. And the goal is, for example, to compute some global property, some predicate or function on the input values which are given to these agents at the beginning. Okay, so this is one of the things we would like to do with in this system, in a very abstract way, of course. So, for example, whether 10% of the population has an elevated temperature or any elevated input value, this can be an example of what we would like to compute. But we will see other things that we would like to compute, more basic primitives. Yeah. So this model was originally motivated by mobile sensor networks, but it also proved to be useful to model other phenomena in other domains of study, like, for example, propagation of trust or epidemics in social networks, or even for modeling chemical reactions, or even to model repetitive games or fan participants in game theory. Yeah. Okay, so I continue with the formal issues of these things of this model. So we have this notion of interaction graph in the model. In this graph, the nodes represent agents, and the edges represent actually the possible interactions between the agents. So an edge can be directed, and this means that in the interaction and the corresponding transition between the two agents, they will be distinguishable. One will take the role of initiator and another one as a responder. That means that even if the two agents have the same state, they can be distinguishable. They can be distinguished. Okay, this is an important point for designing algorithms. This simplifies things. But we can also have graphs which are undirected, and then we say that the interactions are symmetric. And in this case, I mentioned the two agents won't be distinguishable. Okay, so in general, we may have any weakly connected graph of the agents, but frequently, and also in this talk, we'll assume a complete communication graph. Okay, and now how the execution proceeds in such a system, how we model it, how we see it. So in fact, we imagine that there are steps, and at each step, a pair of agents is chosen to interact, to perform a transition according to the protocol, and the whole system after this transition moves to a new configuration. Okay, because a transition it changes the values of the variables of the protocol. So we, in particular, in fact, we can see that all the configuration of the system changes. And I didn't say what is configuration, but configuration is defined as a vector of agent states. Okay, so this is like a snapshot of what we have in the system, all the values of all our nodes, of all our agents. Yeah, so the execution is this infinite sequence of configurations and which are updated by the transitions of the chosen pairs of agents. Okay, so the executions go like this, and to be able to solve some common global tasks in the system and prevent complete disconnection in the system, we have to assume that we choose these agents in some fair way. Okay, so we have this notion of fairness, of fair executions. So, for example, one of the classical fairnesses is to ask that every pair of agents is chosen infinitely often during an execution. We cannot have some pair of agents never executing or executing or doesn't interact infinitely many times. Yeah, every pair has to participate in the algorithm, in the protocol. Okay, we can also ask that each pair of agents is chosen to interact uniformly at random. Or we can also ask that an infinitely often reachable configuration is reached eventually, meaning we cannot prevent that the protocol reach some configuration, some situation, if this situation always was, if we always can reach it. Okay, and another way to see what means this global fairness is to see this result that we have. In fact, probabilistic fairness, an execution satisfying this fairness, probabilistic one, implies, in fact, the global fairness with probability one. Okay, so another way to see global fairness is it's like a simulation of a random environment, but without introducing probabilities in the model. Okay, and I would like to stay a little bit more on these notions because they are important and quite delicate. So I will give you some example now, which will illustrate some better the difference between weak fairness and the two other fairnesses. Okay, so let's take this very simple protocol. So we will have only two possible states for our agents, either white or black. Okay, you can imagine that they have a bit 0, 1. Okay, and there will be only two rules. If two white agents meet, they move to black. And if two agents, one white and another black, meet, they just swap their states. Okay. And now take a very simple system of only 3 agents, like you see here. And let me show you a possible fairly weak execution. So let's assume we start with such a configuration. There are 2 white agents and 1 black. And to satisfy weak fairness, we have to obtain an infinite execution where we have every pair of agents interact infinitely often. Okay, so we start with this first pair of 1 black and 1 white agent. The edges I have here represent interaction. You have understood maybe. Yeah. So we make them interact. They exchange their states. They swap their states. Now we make interact another pair below. Okay. We have this configuration, and we make also interact the third possible pair in this system. And now we repeat the whole scenario infinitely many times. So it gives us an execution, possible weakly fair execution. Okay, so however, this won't be a globally fair or probabilistically fair execution. Okay, this won't be a correct one in the case of global fairness or probabilistic fairness. Why? Because in any point of this execution I just have created, we can make 2 white agents to communicate, right? And then we move to configuration where all the agents are black, and we cannot apply any other rule. Okay, and we stay with such configurations from one step to the other. Agents can interact, but nothing happens. Okay, nothing changes. So with global fairness or with probabilistic fairness, we will eventually have a suffix of execution having this black configuration. Okay, so this illustrates a bit more the difference between these 2 types of fairnesses, and I actually will focus more on the second type of global and probabilistic fairness, which allows us also design more easily algorithms than with weak fairness. We know that randomness simplifies things. Yeah. Okay. And now, yeah. So about complexities, there are two main resources that we care in particular in population protocol. This is the memory space in terms of number of states or bits per agent in the protocol, and also time, okay, in terms of the number of interactions until stabilization to some correct output or good behavior of the system. Okay, so in the case of random fairness or random scheduler, we use also a notion of parallel time, which parallel time actually counted in the number of interactions, but we divide also by n this number of interactions. The reason behind it is that in this case, in case of random scheduler, per parallel time unit, each agent participates in all fun interactions in average. Okay, so just remember that whenever I will speak about time complexity, it is always this number of interaction until the good behavior, until the good correct output divided by n. And now, what means self-stabilization? So this is an approach to deal with failures, with unreliability in the system, or it's also good for systems where the devices are hardly accessible or subject more precisely to, in fact, any number of so-called transient failures. Okay, so transient failures, these are failures like, for example, memory corruptions or corruptions during a communication, or even some topological changes. Anyhow, these failures, we assume that they stop at some moment during the execution, and they, in fact, bring our system in a completely arbitrary configuration. Okay, so we imagine that our system can be brought to some arbitrary configuration with values that we have no control over them, and a self-stabilizing protocol have to recover a correct behavior, reach correct configurations eventually after this arbitrary configuration, and stay correct thereafter, of course, barring additional faults. Okay, so it doesn't mean that in the execution we can have only at some moment the failures. No, we can have them at any time, but we need that these faults stop at some moment. Okay, we have corruptions, we have our system in some arbitrary configuration, but after that moment, if we have enough time without failures, we can recover a good behavior. Okay, so here is an important point that actually our protocols, we cannot initialize them. Like in a classical case of algorithms, normally algorithms, we assume some initialization. And this is a big difference, okay? This imposes, in fact, pretty many challenges in design, in the design of algorithm, okay? So my goal will be to present you such types of solutions in the context of population protocols. And I will start with the first important problem in computer science, counting. Okay, so we will imagine that we have our population, anonymous one, with indistinguishable agents. We don't know, and the agents themselves, of course, do not know what is the size, how many they are, and we want that some agents eventually count the size of the population in some, for example, variable that I will denote by small n. Okay, you see it here. I don't know if you see my pointer. Yeah, but you see this, the variable n, and eventually we want that some agents compute the value of the big N, the actual size of the population. Okay, and our goal will be also to get a self-stabilizing algorithm without any initialization. And unfortunately, we can show relatively easily. I could show you if somebody explain you more in details how we can do it in this question section later. But what I say is that yeah, this is impossible to obtain a solution for this problem using having it purely self-stabilizing. Okay. And the solution is okay. So we cannot allow completely uninitialized solution. We will introduce one particular distinguishable agent. Let's call it a base station or leader. Okay, base station. This is because of the mobile sensor networks motivation, and only this agent will be initialized. Okay, and we let us also assume that this will be this agent that will count the number of the small other agents. Okay, and these other agents won't be initialized. Okay, so it's not a pure self-stabilization, but almost. And another goal is also we would like to design symmetric and deterministic population protocols. So symmetric, this is, I already spoke about that. That means this is more general, of course, than asymmetric. And it means that in our rules will be so that if they take into account two agents that are in the same state, like here state P, they have to move to some maybe different state Q, but both of them to this to the same state. Okay, because these two agents in the same state are actually undistinguishable. We cannot say one moved to one state and another in another state. We may imagine a system where we cannot make to distinguish these agents. We cannot have these different roles of initiator and responder. Some anonymity, particular anonymity, can be desired in the system. Okay. And also a symmetric protocol also will work in an asymmetric environment. There is no problem with that. And we would like to use as much as possible memory space per agent. Okay, but because this may be not the only algorithm that we execute in the system, there may be a lot of others. This is very small building block. So our goal is to minimize the used resources of every sub-protocol, sub-algorithm in our system. Okay, so we would like to minimize space used per an agent. So it's easy to see that if agents have only one state, we cannot solve the problem because the agents become completely undistinguishable for the base station, whether it is one agent or a plurality of agents. It cannot see that, okay, because the agents cannot be noted, okay, I have seen you, I counted you or not, they have only one state. But surprisingly, we can show that only with one bit per agent with two states, we can solve the problem, and I will show it to you how can we do it. And our goal will be also to optimize time for this particular algorithm to count fast. I won't give details about that in the presentation. I just mentioned the result that we obtained, and if you like, I could answer in more details in the question session about that. Okay, just before I move to the details of this solution with only one bit, I give you just a little bit more motivation for counting why this is important. So this is a fundamental and extensively studied task in general in computer science and not only in distributed systems. It is useful in many fields like traffic monitoring, query optimization, and data mining. And for example, in population protocols, we know that counting can be also used to solve other tasks like departition, naming, and degree recognition, and so on and so on. Okay, so now how can we count these small agents which are anonymous, having no identifiers and having only one bit of memory, only two states, either 0 or 1, and which are starts with in an arbitrary state, either 0 or 1. So this is important here that they start like this arbitrary, right? Because if they can all start, for example, if we can make them start from 0, yeah, it's easy to count because the base station just meets every agent and moves the state to 1 and increments the counter. And when all of them move to 1, we know the base station got the correct count, right? So it's easy with initialization, but like this is more complex. Okay, so how the base station can count such agents. So we say that the base station will be the only agent that we will initialize. Okay, so it will have 3 counters, n0, n1, and n. Okay, this is the pseudocode of this is the algorithm. It is very simple. Yeah, so actually the agents themselves, they do nothing. They just interact with the base station, and all the program is actually placed in the base station. So what are these 3 counters? So n0 in fact estimates the number of 0 agents, n1 estimates the number of 1 agents, and n is the sum of the 2. So we update n to the sum of the 2 at each interaction between a base station and an agent. So how the algorithm works? So I will explain it to you using the following example, the following execution. So assume an agent in state 0 interacts with a base station. It flips its state to 1, okay? And whenever it did it, the base station actually understands, okay, the reason of doing what is done in the algorithm is that at this moment, the base station understands that there is one more 1 agent in the population and 1 less 0 agents. So it increments n1 by 1 and decrements n0 by 1 if it's not already 0. Okay, and we continue like this. The base station meets another 0. It makes the same, increments n1. Now we have only 1 agent, and what we will do is we will decrement each time we flip the state of the agent. We decrement the n1 counter and we increment the n0 because we have now more 0 agents. Okay, this is the reason behind. Okay, and I continue like this, and now we got a correct count. But yeah, this is just an example why the protocol is correct for any possible execution. So we can prove it like this. Let's show you the idea of the proof. So first of all, we can easily show that we never overestimate the number of agents in these counters. Yeah, and also that the n, the values of n are never decreasing. Okay, this is the first point that we can prove. But the more interesting thing is that we maybe you could already feel that in the execution of this protocol we may have a lot of cycles, execution cycles. For example, let's take this population of 2x agents that you see here. Assume they all start from 0, and now the base station, let's say, interact only with half of the population, of the subpopulation of size x, and it meets 1 by 1 these agents, and they move to state 1, and then so n1 counter becomes 6. We have seen x agents, this is good, but we can continue to see them again, and we move them to 0. Now the n0 becomes 6 and 1, 0. And now let's perform the same scenario with the other half of the population. Yeah, and we do the same thing, but we do not advance with the counting. We stay with x, but we have 2x agents. So the problem here is because the two halves of the population are completely undistinguishable from the point of view of the base station. And we can cycle like this, we can repeat this scenario, but we cannot do it with global fairness. Yeah? So why? Because there is always a possible scenario that we can apply from any configuration in such an execution, where we make every agent of the whole population to meet with the base station, and then the base station will be able to count all of them. Okay, this is an idea, and to get the correct 2x count. And since this scenario can be applied and we can reach such a configuration from any point, in fact, in any execution, with global fairness, we will reach it. Okay. Before I told you that global fairness is quite similar to the probabilistic one. So now, in fact, if we want to evaluate, to analyze time of this algorithm, we can assume a probabilistic scheduler which chooses the agents uniformly at random, and we can show that unfortunately the stabilization time of this algorithm is exponential. Yeah, so this is not very good, but we can show that we can do better, and we can do better even if we still use only 2 states per agent, only 1 bit. Yeah, and in some work we have shown that if we use only 2 states, we have to use at least n log n expected parallel time to stabilize to a correct count. And we also proposed an algorithm, a protocol that reached this bound. And again, so the very, very high idea of this algorithm is that we control the way base station notes the agents and moves them from 1 to 0, so that we can do it in a more controlled way and prevent from this many cycles possible in the previous algorithm. But I could give you some more details on this idea also during the question session if you would like. And now let me move to another subject, to another problem, which is even more important, and especially in distributed computing, which is called the leader election. I speak in a moment a bit more about the motivation for this problem, but let me explain you what is this problem. So in a very simple form of this problem, we may imagine that our agents are in one of the 2 possible states, is a leader or followers, and we want that eventually, and in the case of a random scheduler with probability 1 in every execution, we obtain a configuration where we have only one and unique agent in a leader state, and we stay like this after forever, and all the other agents are followers. Okay, so we have only one leader. We want to elect a particular distinguishable agent in the population, and only one. Okay, so, and we say that then if we succeed this, we say that at this moment in the execution we have stabilized to a correct output, to a correct leader. Okay. Yeah. So again, this problem has been studied a lot in distributed computing, because when we have a leader, we introduce a sort of synchronization, a sort of centralization in our distributed model. Yeah, distributed is contrary of centralization, but with the leaders, things become more efficient and more easier because we have this coordinator that can coordinate the tasks in the system. And in particular, in population protocols, having a leader, protocols can become indeed exponentially faster, more efficient in space, and even become feasible. So now I will try to explain you how we can solve this problem in different ways. And before I start to speak about self-stabilization, self-stabilizing solutions, which are much more intricate, I will also start. I will start with the initialized case, with the classical type of algorithms where we assume that our nodes, our agents, our system can be initialized. Okay, so this problem was studied also, of course, in this context. So if we assume that we can initialize our agents, let's say we can initialize them all in a leader state, we can solve this problem quite easily using this protocol having only one rule, yeah, which actually says that when two leaders meet, one drops off, one becomes follower. Okay, so the algorithm will proceed in such a way. Okay, and we will get one leader, and we can show that such protocol takes to stabilize will stabilize in linear time in expectation. Okay, and there are even results showing that we cannot do better than linear time. We have to spend at least linear time if we have a protocol that uses a constant number of states per agent. Okay, but if we use just a little bit more, log n states, we can already obtain an optimal and logarithmic time protocol. Okay, so there was a lot of work doing that, and it's quite complex to obtain this optimal result. Yeah, but there was less work about self-stabilization because it is also a bit more difficult. So now I move to the self-stabilizing case. How can we solve this problem starting from any arbitrary configuration? So first of all, let me show you that the previous algorithm, the simple one, two leaders meet, one drops off, doesn't work. It is not a self-stabilizing algorithm. Why? Because if, for example, we start from a configuration where all the agents are in a follower state, yeah, we have no leader, so this rule cannot be applied, right? And we cannot create any leader. So this protocol doesn't help us if we start from a configuration like this. Another result is that we need at least a logarithmic time to produce a leader. For example, if we start from a configuration where all the agents are leaders, at least n-1 agents have to interact at least once to become a follower, right? Because if they don't interact, nothing happens. They stay with the same state. So, and at least n-1 agents have to interact, and with random scheduler, we can show using a coupon collector argument that it takes at least logarithmic time, that it takes logarithmic time. Okay, so we know that our goal is to achieve this time. We would like to make it the fastest as possible, right? So I will show you an algorithm that does this. But before that, unfortunately, there is another negative result for in this case of self-stabilizing leader election, which shows that we have to assume the protocol should be so-called non-uniform. The agents have to know the size of the population. Okay. And to feel why is that? Consider such a stable configuration with n agents. Stable meaning we already assume we have a correct self-stabilizing leader election protocol. We obtain this configuration with a unique leader. You have this leader here. We have n agents. And now focus, so we have this correct protocol, right? So I try to show you things by contradiction to show that we have to know n, okay? Agents have to know the value of n. So if the protocol works without n, we have got this good configuration with the leader, and now we focus on these n-1 agents, which are followers, right? So these agents cannot anymore create any leader, right, with the same protocol. So if we imagine now a population of n-1 agents that start from these states, with the same protocol, we cannot obtain a correct solution. We won't create any leader. So this means that agents have to know in some way that they are the population is of n-1. Okay, this is not exactly the proof, but this gives an idea why this protocol cannot be non-uniform, and we have results that shows that we have to know the number of agents, the size that the agents have to know the number of the size of the population incorporated in the protocol. Okay. Okay, and now the first self-stabilizing leader election protocol that appeared was not that efficient. I will speak in a minute what is its stabilizing time. But we had this algorithm which is a self-stabilizing one. So in this algorithm, agents can be in one of the n states. You see here is from 0 to n-1, and the 0 state is considered to be a leader. Okay, so if there is an agent at 0 state, we think of it as a leader, right? And the protocol was simple. There was only one type of rules. If two agents in state S meet, one of them becomes S+1 modulo n. Okay, so you may imagine some arbitrary configuration. Yeah, this is self-stabilization. Like here, 2 agents in state 1, 3 agents in state 3, 2 agents in state 5. 2 of them in state 3 meet, and 1 becomes 4. And we can continue applying the same rule. And what happens, we can show that eventually each of these possible states from 0 to n-1 will be taken by one of the agents. So in particular, there will be an agent in state 0, only one, and this one will be the leader. Okay, so this is why this algorithm solves leader election. And in fact, we can also see that we can rank in such a way our agents from 1 to n. So we also say a so-called ranking problem, which is strictly harder. And we can show that this protocol is, however, have a stabilization time of n to the 2 parallel time. Okay, and now I will show you another protocol that solves the same problem and also a ranking problem, but in a logarithmic time. Okay, so remember that also in this algorithm we made a sort of naming of our agents and also a ranking, okay? And because we have ranking, this is easy to fix, for example, the agent eventually with rank 1 as a leader. Okay, so how can we do leader election in a self-stabilizing way in population protocols or in only logarithmic time? Okay, so let me present you this solution. So in this algorithm, agents will be in two main states, either collecting, either resetting. So when they are collecting, an agent has a name taken from a set 1 to n to the 3. And each agent also in this state has a roster array. Okay, there is an array where each agent tries to collect the names of the other agents in the population. And how it collects it? By merging during interaction, the two agents will merge their rosters to the same names. You have seen they had 5 and 11 and 4, and now both of these interacting agents has the same name. So we merge the rosters in such a way during the meetings, and so in fact we we realize here what is called also epidemics. We actually propagate the names, the content of the rosters to the whole population, okay? And this primitive of epidemics, we just use it here. We know that it takes to propagate each name in such a way in logarithmic time. Okay, so we know that propagating all the names of all the rosters in parallel takes this time. Okay, it's not an easy result, but we can prove that it takes this time. So I try to show you how we merge the rosters. And what is important that whenever an agent, so agents know n, they know the size of the population, and when a roster of an agent becomes exactly n, it can obtain ranks of the names in the roster. It order the roster in a lexicographical order, and for example, this agent 4 here, it knows that its rank is 2, okay, because his name is the second in the lexicographical order in the roster, and it knows also that for the moment it estimates that the leader is the agent with the name 2. Okay, we say that the first rank will be given to a leader. Okay, so this what happens more or less during a collecting state, what we do and how we launch actually a reset. When agents move to a resetting state, so they move to the resetting state. They trigger a reset whenever a so-called ghost name is detected. So what is a ghost name? It is in fact a name that doesn't belongs to any agent in the population. This name appears in the roster of some agent, but there are no agent with this name. So if there are no homonyms, if there are no agents with the same name, eventually we are sure that some agent will obtain a roster which will be bigger than n, and this will trigger a reset. This will signal mean that there are ghost names. So like in this example, you can see that there are no agent in state with the name 11, but in the roster of agent 4, we have this name 11. When 4 and 10 meet, they will change their rosters to be of size 6 already. They know that the population is of size 5. They will trigger reset, okay? And we also trigger reset if we detect name collision. So in case we two agents in the same state meet, we trigger a reset. But notice that to wait that only 2 existed homonyms in the population meet, this is very costly. Okay, this takes more than logarithmic time, this takes linear time. And I will show you later how we prevent, how we can accelerate detecting collisions. How we can make it more faster than linear. Okay, so I'll explain you in a moment. But before that, what happens during the reset? So we will trigger a reset in some particular cases, and what will happen is that the 2 agents that meet and detect a problem, they trigger the reset, they move to the resetting state, and they start a counter of a logarithmic size, which is decremented each time during the execution, during the propagation of the reset. And we can show that in a logarithmic time, all these counters will become 0 and all the agents will move to the resetting state. And at that moment, when a counter of an agent in a resetting state becomes 0, agent moves to collecting. And when it moves to collecting, it removes everything from its roster and it picks a new name. Okay, and it picks a new name from this set of n to the 3 names. Again, this is important. This is a big enough set to show by birthday paradox argument that at this moment, every agent on the population of size n will pick with high probability will pick a unique name. Okay, there will be no collisions in the names. Okay, so at the end of the reset, if every agent resetted, we have unique names, and if everything is good, the reset takes logarithmic time, then the propagation of the names with merging of rosters also takes logarithmic time, and at the end of that, we can obtain the leader, the ranking, and what we need. Okay, but remember there was this problem with detection of homonyms. Okay, so what happens if the roster never becomes n and we have homonyms? Because we may have, for example, a population of size 5, and to have 3 agents started with the name 5, let's say 2. Okay, so the roster will be maybe of only two values, right? And so it never will become 5 or 6, for example, or 7. We have to detect the homonyms, and if we only have only 2 homonyms, to make them meet, okay, imagine we have only 2 agents with some name A. To make these agents meet takes with high probability a linear time. This is a time bottleneck, okay, for our solution. We cannot use it because we want to do things in logarithmic time. So we will, I will show you how can we detect such homonyms in a so-called indirect way. Okay. So before that, I will show you an algorithm that can do it, but faster than linear time, in square n time, but not yet logarithmic. And we will use this idea to obtain our logarithmic solution. So the idea is that whenever any 2 agents meet, yeah, they generate a random value that we can call sinc, okay, a common random value out of the set 1 to the k. Okay, k is defined in some efficient way. Okay. And they store this value, both of them, the same one, in some dictionary. So the sinc value S1 that was generated between A and B is stored in the dictionary of B, and of course A makes the same. Yeah, and at the beginning of every interaction, 2 agents first, in fact, will check whether the corresponding sync values stored in both of the dictionaries are the same. So whether S1 is equal to S prime 1, okay? And if they are not the same, reset will be triggered. Why? Because it can happen with probability 1 minus 1 over k if there are homonyms, yeah, and in time square root of n time, some agent will meet such homonyms, and with this probability I mentioned before, the sync values during these two meetings will be different, okay? And the agent will detect in such a way that there are agents with the same name in the population. But once again, this takes not logarithmic time, it takes square and root of time. Just for safety, notice that whenever there are no homonyms, all the agents have unique names. They always generate, any pair of agents generate always the same sync value. Okay, so we will never trigger reset. Okay, this is why I say that. So this is good. We want to stop at some moment to generate reset, to generate new names and change our leader. Yeah, this is why this is important. But how can we accelerate this? So the idea is to keep not only the very last sync value that a couple of agents generated, but also keep the historical values of the sync values of other interactions, of the interaction of this other agent with others, and so on, in a tree-like structure. So each agent will keep such historical sync values in each agent X in a tree rooted in X. Okay, and what is important, and that it will take care that in each leaf to root path there are only unique names that appear, and on the edges we have these sync values that were generated before by the agents. So how agents adopt and update their trees? So let's take these two agents 4 and 11 with these trees you see. So agent 11 during this interaction will add the tree of 4. Okay, I just copied the tree of 4 here. It will add it, link it with one edge. It will generate, 11 will generate together with 4 this sync now value as star, and remove to keep on the unique names on each path, leaf to the root path. We will remove all the subtrees that are rooted in 11. Okay, this will ensure that we have always such passes with unique names. And 4 will do a similar thing. It will add the tree of 11 with the same generated common sync value. And there are no any trees rooted in the subtrees rooted in 4, so nothing happens. So this is how agents update their trees during the interaction. And we can observe that, we can prove that after logarithmic time of such updates of trees, so first of all, the trees have to be of depths of logarithmic depths 2. After logarithmic time, we could detect, we could obtain information in trees, in a tree of some agent regarding some name collisions, the existence of homonyms. Okay, after logarithmic time, there will be we could obtain the required information about that. So how agents detect, what they check detect such collisions, such problems, the fact that there were homonyms. So assume we have these two agents 5 and 4. What 5 will do, asymmetrically 4, of course, it will check all the passes, leaf to root passes that end up by 4, and it will take in such passes the sub-passes that appear also in the tree of 4. Okay, so I noted such a pass from 3 to 4, and 5 will check whether S1 equal to S prime 1, whether S2 equal to S prime 2. And if all the couples of sync values are different, it will trigger a reset. Okay, so if for some, at least for some couple, the sync values correspond, they are the same, then there will be no name collision. Okay, and why? Because imagine that if all the two couples of sync values here are both not correspond, they are not the same. It should mean, but if we have no homonyms in the population, there are only 1 for age, and we cannot have this. Why? Because in fact what will happen is that if they all different, that means that 4, 2, and 3 have met after 6 met 3 with these values. Okay, and this is because why there were new sync values that were generated, but that means that but before 6 met 3, and the sync value between 6 and 3 will be the same and will be in the tree of 4. Okay, it's a bit difficult to show, but I hope you could probably understand that in such a way, by keeping historical sync values in such a way, we could detect that the several agents with the same name, and so the sync values are not completely synchronized. Okay, so this is the idea of the algorithm, and once again we can show that this is enough to keep such trees of depths, of the logarithmic depths, and this also we can show takes a logarithmic time to get such trees. And now we can, I will do some summary of the time analysis. So once again, to detect ghost names, we have shown by merging rosters takes logarithmic time. To detect collisions of homonyms takes also logarithmic time. So these are the two problems that we can have that will prevent from having unique names, creating, having ranking and leader elections. So these are two things that we have to detect. I showed you how we can detect this fast, and reset also takes logarithmic time. And after the reset, I showed you that every agent pick a unique name, and then in logarithmic time, all the names are propagated, and we obtain ranking and leader election. Okay, and regarding the space complexity, so in fact, the tree structure is the most important. It takes most of the space. All the other fields are negligible comparing to this tree structure. So regarding the tree, then the trees are of depths, of logarithmic depths. Each node can have at most n children. So we have n over log n nodes, all of that in the tree, and each node keeps the name, the roster, sorry, the name in the tree is only the name, also the sequence, the sync value, and all this takes no more than logarithm log of n. So this is why we have this number of bits, which is of course in number of states it is exponential on that. Okay, so yeah, so in terms of space, there are still places to improve or prove that we can do better. And now let me conclude. So we have seen how we can solve counting in a almost self-stabilizing way in a using only 1 bit per agent, and also how can we do it optimally in time. And we just have seen how we can solve self-stabilizing literal action or ranking in logarithmic time. But you have felt that self-stabilization is not easy, in particular on population protocols, and we indeed I have shown you several impossibility results, but there are many others. We know, for example, that in the original population protocols in complete graph with constant memory agents, we cannot we cannot compute many functions, in fact only constant, almost only constant ones, which are not that interesting, and we have many other impossibilities for other problems like naming and degree recognition and others. So the scientists wanted to see what should we add to the model, to the system, to be able to produce and to design self-stabilizing solutions. So some have added some sort of synchronization in the interaction scheduling, like k-wise interaction instead of pairwise, or introduce some synchronous rounds in the system, and so on. Some assumed particular topologies like ring or regular graphs, and others introduced more memory or introduced more less uniformity, like we have seen here, introducing a leader or base station, or introducing more names, and so on. And just another way.
Janna, I'm sorry to say we've run out of time.
Okay.
I think we could continue the next few slides in the discussion zone. You will be able to share it in Zoom Meet. So thank you for amazing talk.
Okay.
I do invite everyone to the discussion zone. We'll probably finish the talk and you'll have the opportunity to ask your questions. Thank you.
Okay, thank you. Thank you very much.